Hello everyone, welcome to our chemistry class. Now today's lecture will be mainly focused on how to find the molecular structure, that is structure or the geometry of molecules and its hybridization. So along with this, we'll try to find out the total number of electron pairs present in the valency shell of the central atom. Out of this total number of electrons, how many of them are involved in bond formation known as bonded pair of electrons, and how many of them are left unused after chemical bond formation, that is lone pair electrons. So having learned this hybridization, we have a bit knowledge about the concept of hybridization. Now in this, we'll also find out the hybridization and the geometry shape of the molecules. So the heading will be molecular geometry or structure. Now to find the structure or the geometry of a given molecule or an ionic species, किसी भी molecule or ionic substance का structure निकालने के लिए we have to use a particular theory, and that theory is known as VSEPR theory. The full form of this VSEPR is V stands for valency, S stands for shell, E stands for electron, P stands for pair, R stands for repulsion. So valency, shell, electron, pair, repulsion theory. This is the theory by use of which we can predict the structure, geometry of any given molecular species or ionic species. So let's explain what is this VSEPR theory. Now this VSEPR theory is based on this premise that the electron pairs present in the valency shell of a central atom undergoes the repulsion. Now to minimize the repulsion between these electron pairs are arranged in such a way that the distance between the electron pairs should be maximum. As the distance is maximum, the repulsion factor between these pair of electrons will be minimum. So that minimum repulsion will be the most stable arrangement of electron pairs, and that stable arrangement of electron pairs around the central atom gives rise to the molecular geometry or the structure. So the first thing is the electron pairs present in the valency shell of the central atom undergoes repulsion. To minimize this repulsion, they are arranged at a greater distance or the maximum distance. When they are at maximum distance, the angle between the bond pairs of electrons will also be maximum. As the distance is maximum, the repulsive force will be minimum, or the potential energy of the system will also be minimum to give you the more stabilized arrangement of electron pairs. So the first point is the electron pairs present in the valency shell of central atom undergoes a repulsion to minimize the repulsion. The electron pairs are arranged in such a way that the distance between them is maximum. So as the distance is maximum, angle between them will also be maximum. As the distance is maximum or the angle between them is maximum, the repulsive force will be minimum. As the repulsive force is minimum, the potential energy of the system will be minimum. As the potential energy of the system is minimized, this gives rise to the most stable arrangement. This most stable arrangement of electron pairs gives rise to the molecular structure. So in a way, simply saying the molecular structure is nothing but the relative arrangement of the electron pairs present in the valency shell of an central atom in a given molecule or in an ionic species. So the condition for this arrangement of electron pair is distance between them should be maximum. As the distance is maximum, the angle between the pair of electrons should also be maximum. As the angle is maximum, the repulsive force between the electron pairs will be minimum. As the repulsive force is minimized, the potential energy of the system will also be the least, and that particular form is known as the most stable arrangement of electron pairs, and that gives rise to the molecular structure, shape or geometry. So this is the very important postulate or the premise of this valency shell electron pair repulsion theory. Now coming to the second point. Now the central atom of any given molecule or an ionic species may have two types of electron pairs. One is known as bonded pairs of electrons, which are involved in chemical bond formation. The other one is lone pair of electrons. Those electrons which are left outside the bond formation are known as lone pair electrons. So the repulsive force, the order of repulsive force between the electron pair is the maximum in case of lone pair and minimum in case of bonded pair and bonded pair. So we have this electron pairs. These electron pairs are of two types: lone pair, short form LP, then we have bonded pair, short form written as BP. So these bonded pair is pairs of electron involved in bond formation. Electron pairs involved in bond formation are known as bonded pairs of electrons, and those electrons which are left after formation of bond, these are known as lone pair electrons. Electron pairs left after bond formation. So we have these two pairs of electrons, and the order of repulsion of various lone pair is electron pair is lone pair repulsion is the having the maximum value, followed by repulsion between lone pair and the bonded pair, followed by repulsion between bonded pair and the bonded pair. So maximum repulsive force is felt between lone pair and lone pair, and the minimum repulsion in case of bonded pair and the bonded pair. So the reason for this is, now these lone pair, as I have mentioned you earlier, these are the electron pairs left unused after chemical bond formation. So these electron pairs being left unused will try to occupy maximum space. When these try to occupy maximum space, the repulsive or distance between the electron pairs will be minimum. As the distance is minimized, the repulsive force will be more. So the reason for lone pair having maximum repulsion is these lone pair tries to occupy maximum space or volume. Tries to occupies maximum space or volume. So when this occupies maximum space, maximum available space around the central atom. So when this try to occupy maximum available space of the central atom, the distance between the electron pairs will decrease. As the distance between the electron pair is decreased, the repulsive factor will be more. On the other hand, the bonded pairs of electrons are having the least repulsive factor. The reason for this is bonded pairs of electrons are fixed in between the two combining atoms. As a result, they cannot occupy the maximum space, or they cannot expand the space, or we can say they occupy the least space. So the reason is these bonded pairs are fixed between the two atoms and occupies the least space or volume. Hence, the order of repulsion is minimum in case of bonded pair. So this is the order of repulsion. So because of this repulsion, we get different types of shapes, molecules, shapes, structure, geometry, etc. So this is the second point. The third point of this valency shell electron pair repulsion theory, this can also be considered as one of the important demerits of this theory. This theory says, or this theory considers, all the bonds formed by the central atoms are single bonds only. Even if the molecule contains double bond or triple bond, this double bond or triple bond is assumed to be single bond. So write down. Theory considers only single bond even if the molecule contains double or triple bond. Even if the molecule contains double or triple bond, it is assumed to be single bond. So this point is one of the postulates of VSEPR theory as well as one of the important demerits of this VSEPR theory. Considered as demerit of theory. So this is the important postulates or the premise of valency shell electron pair repulsion theory. Now coming to how to find the number of electron pairs present in the valency shell of the central atom, and from this we have to find how many of them are involved in bond formation, how many of them are involved in not involved in bond formation, and how many hybrid orbitals should be formed by the central atom, and what should be the hybridization of the central atom. Once we know the hybridization, we can easily predict what is the shape, geometry, and what is the shape of molecule. Now coming to the calculation of number of electron pairs present in the valency shell of the central atom. Calculation of electron pairs present in the valency shell of central atom. Let the number of electrons present in the valency shell be n, then n by 2 represents the electron pairs. If n is the total number of electrons present in the valency shell, then n by 2 represents the electron pairs present in the valency shell of central atom. So this n by 2, or the number of electron pairs present in the valency shell of central atom, is defined as number of electrons in the valency shell of central atom in the ground state, number of electrons present in the valency shell of central atom in ground state, plus the number of other atoms bonded to central atom except oxygen. Now the contribution of oxygen is ignored, the reason being oxygen forms multiple bonds. So except oxygen, we have to include the contribution of the electrons coming from the other atoms. So number of electrons in the valency shell of central atom plus number of other atoms bonded to the central atom except oxygen. Then we have plus minus net charge. That means we may have an ionic species. If ionic species, then we can have positively charged or we can have negatively charged. If the ion is positively charged, for every positive charge we have to subtract -1. So -1 is for positively charged, we have to subtract the positive charge. If the ionic species is negatively charged, for every negative charge we have to add +1. So plus is for negatively charged species, minus is for positively charged species. And all these value, this summation of these three should be divided by 2. So this gives you the total number of electron pairs present in the valency shell of the central atom. Now from this we have to define the number of bond pairs, number of lone pairs, total number of hybrid orbitals required, and what is the hybridization involved in bond formation. So I'm repeating, this is the number of electrons present in the valence shell of central atom in the ground state, plus the number of other atoms bonded to the central atom except oxygen. We are not including oxygen because oxygen in most of the case forms multiple bond. Plus minus net charge. This plus charge is for Ni. For every negative charge we have to add plus 1. Negative charge is for positively charged species. So for every positive charge we have to subtract 1. All this divided by 2, this gives you electron pairs. Now this total number of electron pair is n by 2. So these n by 2 contains lone pairs or bond pairs. So out of these, the number of bonded pairs is equal to the number of other atoms. So the total number of bonded pairs will be equals to the total number of other atoms bonded to the central atom, because all these other atoms forms a covalent bond with the central atom. So whenever there is a formation of a covalent bond, a pair of electron is involved or a pair of electron is shared between the combining atoms. तो जितना बॉन्ड से उतना ही आपके पास बॉन्ड पेयर्स होगा, बिकॉज एक बॉन्ड में आपके पास एक पेयर ऑफ इलेक्ट्रॉन्स कंपल्सरी शेयर करेंगे. तो टोटल नंबर ऑफ इलेक्ट्रॉन पेयर में से बॉन्डेड पेयर्स कितना हुआ, जितना अदर एटम सेंट्रल एटम में जुड़ा हुआ है. देन number of lone pairs is equal to this total number of electron pairs minus number of bond pairs, because this electron pair is summation of lone pairs and bond pairs. तो जितना इलेक्ट्रॉन पेयर है उसमें से अगर बॉन्डेड पेयर्स और जितना बॉन्ड्स माइनस करेंगे उतना आपके पास लोन पेयर इलेक्ट्रॉन्स, अनयूज्ड इलेक्ट्रॉन्स सेंट्रल एटम के पास बचा हुआ है. नाउ ये जो जितना इलेक्ट्रॉन पेयर्स है, दिस टोटल नंबर ऑफ इलेक्ट्रॉन पेयर्स, बिकॉज लुक एट दिस, सेंट्रल एटम के पास इतना इलेक्ट्रॉन पेयर्स प्रेजेंट है. तो जितना इलेक्ट्रॉन पेयर्स प्रेजेंट है उतना आपके पास हाइब्रिड ऑर्बिटल्स होना पड़ेगा, बिकॉज एक ऑर्बिटल में मैक्सिमम 2 इलेक्ट्रॉन्स रख सकते हैं, मींस ए पेयर ऑफ इलेक्ट्रॉन. इफ देयर आर 5 इलेक्ट्रॉन पेयर्स है, देन मिनिमम 5 ऑर्बिटल्स आपको चाहिए, ताकि एक ऑर्बिटल में एक इलेक्ट्रॉन पेयर्स रखेगा. इफ द नंबर ऑफ इलेक्ट्रॉन पेयर्स 3 है, देन हाउ मेनी हाइब्रिड ऑर्बिटल्स रिक्वायर्ड? 3 hybrid orbitals चाहिए, because each hybrid orbital will occupy a pair of electrons. So the number of electron pairs is equal to number of hybrid orbitals required. इसका मतलब अगर जितना हाइब्रिड ऑर्बिटल्स चाहिए उतना आपके पास एटॉमिक ऑर्बिटल्स मिक्स करके हाइब्रिड ऑर्बिटल्स बनाना पड़ेगा. वंस वी नो द नंबर ऑफ हाइब्रिड ऑर्बिटल्स रिक्वायर्ड, देन मेरे पास हाइब्रिडाइजेशन मिल गया. तो वंस आपके पास हाइब्रिडाइजेशन मिला तो वी कैन गेट इस ज्योमेट्री एंड द शेप ऑफ मॉलिक्यूल. सो let me just explain you the difference between the shape and the geometry. Geometry is three-dimensional arrangement of all electron pairs, that is lone pair and the bonded pairs, around the central atom. जितना इलेक्ट्रॉन पेयर्स प्रेजेंट है अगर उसको अरेंज करते हैं तो दैट गिव्स राइज टू ज्योमेट्री. वेयर शेप का मीनिंग ये अरेंजमेंट ऑफ ओनली बॉन्डेड पेयर्स ऑफ इलेक्ट्रॉन्स. सिर्फ बॉन्डेड पेयर्स ऑफ इलेक्ट्रॉन्स को अगर अरेंज करना है तो दैट गिव्स राइज टू द शेप ऑफ मॉलिक्यूल और शेप ऑफ आयन। तो हमें दोनों को डिफाइन करना है, शेप क्या होगा, ज्योमेट्री क्या होगा। इफ द मॉलिक्यूल डज नॉट हैव लोन पेयर देन शेप और ज्योमेट्री सेम होगा। तो यहां पे लिखिए if the molecule does not have lone pair then geometry and shape both are same or identical. But if the molecule contains lone pair then geometry and shape will be different. If the molecule contains lone pair then geometry and the shape are different. So please keep in mind these two. So again I am repeating, geometry is the complete arrangement of all the electron pairs including lone pair around the central atom, whereas shape means only the arrangement of bonded pairs of electrons around the central atom. So this is how we define lone pairs of electron. From these lone pairs of electron we can define how many bonded pairs है, कितना bonds बना हुआ है और कितना lone pairs है। उसके बाद जितना इलेक्ट्रॉन पेयर्स है उतना आपको हाइब्रिड ऑर्बिटल्स भी चाहिए, बिकॉज एक हाइब्रिड ऑर्बिटल्स में एक पेयर इलेक्ट्रॉन रख सकते हैं। अब जब आपके पास हाइब्रिड ऑर्बिटल्स कितना चाहिए वो बना, उसके बाद तो आप लोग बता सकते कि व्हाट इज द हाइब्रिडाइजेशन, बिकॉज अगर दो चाहिए तो दो हाइब्रिड ऑर्बिटल्स बनना पड़ेगा, दो बनाने के लिए दो एटॉमिक ऑर्बिटल्स मिक्स करेंगे। इस तरह से जब हाइब्रिडाइजेशन मिला देन आपके पास ज्योमेट्री, शेप एज वेल एज द बॉन्ड एंगल ये सभी आपके पास मिल जाएंगे, बिकॉज मैंने आपको हाइब्रिडाइजेशन सिखाया था, उसमें ये भी बताया था हाइब्रिड ऑर्बिटल्स का अरेंजमेंट कैसे होता है और उसका थ्योरेटिकल बॉन्ड एंगल कितना होना चाहिए फॉर डिफरेंट टाइप्स ऑफ hybrid orbitals. So this is how we define the number of electron pairs. Now let's apply this in defining all these parameters. तो for such molecules with only bonded pairs of electrons, molecules with only bond pairs of electrons means there is no lone pair of electron. तो मैं कुछ ऐसा मॉलिक्यूल्स बताऊंगा जिसमें लोन पेयर है ही नहीं, सिर्फ आपके पास बॉन्डेड पेयर है। तो इन सभी के लिए स्ट्रक्चरल ज्योमेट्री कैसे डिफाइन करेंगे। तो फर्स्ट we represent this by A, B, X, where A central atom, B other atom, and X is number of other atoms. A general representation है। We'll take up one by one. Let's take up this AB2 type. The best example is BeCl2, BeH2, BeBr2, BeI2, HgCl2 etc. ये सब एग्जाम्पल्स हैं। नाउ विल टेक अप दिस BeCl2, इसके साथ एक्सप्लेन करेंगे। नाउ इफ यू लुक एट दिस BeCl2, बेरिलियम जो कि लेस इलेक्ट्रोनेगेटिव एटम है, दैट इज योर सेंट्रल एटम. Ca stands for central atom. So we represent this by Ca, other atoms by OA. So we have this Ca, then Cl is other atom. Now let's try to find out the number of electron pairs. So number of electrons in the valence shell of beryllium. Beryllium atomic number 4, so electronic configuration is 1s2, 2s2. We have 2 electrons in the valence shell. So the number of electrons in the valence shell is 2. Now number of other atoms is 2 chlorine, so we have 2 chlorine. The molecule is a neutral, so plus minus 0. Divided by 2, so we have 2 pairs of electrons. So this molecule BeCl2 central atom beryllium के पास 2 pairs of electron है. Now from this हमको डिफाइन करना है कि बॉन्डेड पेयर्स कितना है, लोन पेयर्स कितना है. नाउ अब ध्यान से देखिए, इसमें नंबर ऑफ अदर एटम्स कितना है, 2. इसका मतलब मिनिमम 2 बॉन्ड्स बनना होगा. अगर 2 बॉन्ड्स है तो हाउ मेनी इलेक्ट्रॉन पेयर्स बॉन्ड बन गया, 2 पेयर्स ऑफ इलेक्ट्रॉन्स बॉन्ड बन में इन्वॉल्व हुआ. तो नंबर ऑफ इलेक्ट्रॉन पेयर इज 2. देखो लोन पेयर कितना हुआ, 0, ताकि दोनों सम के बराबर ही. अच्छा, नंबर ऑफ ऑर्बिटल्स सॉरी इलेक्ट्रॉन पेयर 2 है, तो कितना हाइब्रिड ऑर्बिटल चाहिए, 2 hybrid orbitals required. If suppose 2 hybrid orbitals required, then hybridization is, बस सिर्फ मुझे 2 चाहिए, 2 के लिए क्या बनना पड़ेगा, sp. तो 1s and 1p ओवरलैप करेंगे तो कितना हाइब्रिड ऑर्बिटल्स बनेगा, 2sp हाइब्रिड ऑर्बिटल्स बनेंगे. तो once we have this sp, the structure or the shape will be, we have this beryllium, so this is Cl, this is Cl, this is undergoing sp, so sp is a linear, so the bond angle, that is chlorine beryllium bond distance, this bond angle, this is 180, and the molecule is known as linear shape or geometry. So this is the shape, geometry, structure, bond angle, hybridizations, number of hybrid orbitals required, bond pairs, lone pairs, and calculation of electron pairs. So you can take up any of this and you can find easily this. Second type, AB3 type. Example, SO3 BX3, where X is fluorine, chlorine, bromine, iodine, boron trihalides. SO3 sulfur trioxide. So let's take up this sulfur trioxide. So sulfur being the less electronegative, so this sulfur is your central atom. So therefore the electron pairs will be, sulfur is group 16, so we have 6 electrons in the valence shell. Number of other atoms except oxygen, so we have this oxygen, so contribution of oxygen is 0 divided by 2, so this equals to 3 pairs of electron is present in the valence shell of the central atom sulfur in sulfur trioxide. So now look at this, the number of other atom is 3, so we have 3 bond pair, so the number of lone pair is again 0. Now we are excluding the contribution of oxygen, but oxygen is other atom, so we have to count the other atoms as 3. So the number of bonds formed between sulfur oxygen should be 3. Number of lone pair is 0. Now since total 3 electron pairs is present, so we require 3 hybrid orbitals is required. Now, as the 3 hybrid orbital is required, the hybridization of the molecule central atom will be sp2. So, one s orbital combines with 2p orbital to give you 3 equivalent sp2 hybrid orbitals. So, since we are having sp2, so sp2 the most stable arrangement is plane triangular. So, therefore, look at this, we have this sulfur, we have this oxygen, oxygen, oxygen. So, if you join this gives you an equilateral triangle, and the bond angle, that is oxygen sulfur oxygen bond, this is 120, that is planar or triangular, planar or plane triangular. So AB3 type without any lone pair structure is planar or triangular planar, bond angle is 120, hybridization is sp2. Now coming to AB4 type, base example is CH4, NH4 positive, CCl4, BF4 minus, etc. So we can have a more number of examples. I am just giving you some examples. So which one will take up? Let's take up this BF4 minus. To explain this, AB4, BF4 minus. So boron being the less electronegative, so this boron is central atom, and the number of electron pairs around this central atom, boron group 13, so the number of electrons in the valency shell is 3. Now number of other atoms is 4. Now this is an ionic species, we have a negative charge. For this negative charge we have to add 1. So every negative charge add 1, every positive charge minus 1. 2. So this comes out to be 4 electron pairs. Now look at this, the number of other atoms bonded to central atom is 4, so we should have 4 bonded pair, so the lone pair electron will be 0. Now since the number of electron pair is 4, so we require 4 hybrid orbitals, so hybridization is sp3. So sp3, the geometry is tetrahedral, so we have B, F, 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 and this carries a negative charge. If we join this gives you a tetrahedron, and boron occupies the center of tetrahedron, and each and every bond angle, that is FBF, that is 109.5, and the structure is known as tetrahedral. I'll just give you one positive one. So NH4, nitrogen is central atom, so we have N by 2. Nitrogen is group 15, so we have 5 electrons in the valency shell. Number of other atom is 4, but we have a positive charge, so for this we have to subtract 1. So again this comes out to be 4. So everything remains identical. So bonded pair is 4, lone pair is 0, hybrid orbitals required is 4, hybridization is sp3. So everything remains same. So we can easily predict. Next, AB5. Example is PCl5 SbCl5 AsCl5 SOF4. So these are some of the examples of AB5. So let's take up this to explain the structure. We'll take up this structure. So first let me take up this PCl5. So we have PCl5. Phosphorus is the central atom because this is the less electronegative, so number of electron pairs in the valency shell of central atom. Phosphorus 15 group, so we have 5 electrons. Number of other atoms is 5 divided by 2, so we have 5 electron pairs in the valency shell. Number of other atoms is 5, so we have 5 bond pairs and 0 lone pair. Since the number of electron pair is 5, so we require 5 hybrid orbitals. So the hybridization is sp3d, 1s, 3p and 3d orbitals mixed to give you 5 equivalent sp3 hybrid orbitals. To sp3, the shape or structure is triangular bipyramidal. So we have phosphorus, now we have this Cl, I am spelling this Cl as A, this Cl A, Cl E, Cl E, Cl E. Now this is triangular bipyramidal. Triangular bipyramidal. We have 3 types of bonding. This is 180 degree, this is 120 degree, this is 90 degree. Now, as we have discussed earlier while explaining the hybridization, now this A stands for axial bond, E stands for equatorial bond. Now PClA bond is greater than PClE bond length. The reason is 90 degree repulsion. So this is undergoing 90 degree repulsion. Because of this repulsion, bond length increases. Now if axial bond is longer, then this PClA bond is जिसका बॉन्ड लेंथ ज्यादा होगा, बॉन्ड स्ट्रेंथ कम होगा और बॉन्ड रिएक्टिविटी ज्यादा होगा. So axial bond is more reactive than equatorial bond. Bond strength, so ये दोनों का कंपैरिजन है. So this occurs only in triangular bipyramidal geometry. Now coming to this, let me explain. SOF4, sulfur is central atom, so number of electron pairs is sulfur 16 group 6 electron, oxygen 0 plus 4 fluorine divided by 2, so we have 5 electron pairs present in the valency cell. Number of other atom is 4 fluorine plus 1 oxygen, so we have 5 bond pairs and lone pair 0. Since number of electron pair is 5, so we require 5 hybrid orbitals. So the hybridization is sp3d. Now in the first case all the groups are identical, but in the second case we have two different groups, oxygen and the fluorine, having different electronegativity. So we have sulfur, so everything remains same. Now the point that I am going to make here is, in triangular bipyramidal geometry, the most electronegative atom will always occupy the axial position and the less electronegative atom will always occupy equatorial position. So oxygen cannot occupy axial, oxygen has to occupy equatorial. So in triangular bipyramidal, most electronegative atom will always occupy axial position and the least electronegative atom will occupy equatorial position. So please keep this in mind. That is only for trigonal bipyramidal geometry. So this is AB5. Now coming to AB6 type. So second is AB6 type. Example is SF6 PCl6 minus, etc. Now we'll take up this SF6. Sulfur is your central atom because this is the less electronegative. So the number of electron pairs present in the valency cell is sulfur 16. So we have 6 electron. Fluorine 6, so 6 other atoms divided by 2, so we have 6 electron pairs. Number of other atom is 6, so the number of bonded pairs is 6. Number of lone pair is 0. Now since total electron pair is 6, so we require 6 hybrid orbitals, so the hybridization is sp3d2. 1 s orbital, 3 p orbital and 2 d orbital mixed to give you 6 equivalent sp3d2 hybrid orbitals. So sp3d2 means we have octahedral geometry, so we say sulfur lies at the center of square plane, 1 above the plane, 1 below the plane. So this is fluorine, 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 fluorine. And we have two types of bond angle. This is 180 degree, this is 180 degree, this is 180 degree. Rest are 90 degrees. Now this is what we call as octahedral. So in octahedral, there is no equatorial, no axial. All SF bonds are identical. Why? Because this is 90 degree. This is also 90 degree, this is also 90 degree. So there is no difference in the repulsion. So both are identical. So there is no question of axial or equatorial in octahedral geometry. Then we have AB7, and the only example is IF7, iodine heptafluoride. So IF7, let's take this IF7 iodine, जो लेस इलेक्ट्रोनेगेटिव है, ये आपके पास सेंट्रल एटम हुआ. सो वी हैव सेंट्रल एटम. सो नंबर ऑफ इलेक्ट्रॉन पेयर्स कितना हुआ? Iodine 17th group, so 7 electrons in the valence shell. Other atoms 7 divided by 2, so we have 7 electron pairs. Number of other atom is 7, so we have 7 bonded pairs, 0 lone pairs. Total electron pairs 7 है, तो कितना ऑर्बिटल्स चाहिए? 7 हाइब्रिड ऑर्बिटल्स चाहिए. अब ये 7 हाइब्रिड ऑर्बिटल्स तभी बनेगा जब आपके पास sp3d3 टाइप हाइब्रिडाइजेशन होगा. अब sp3d2 में आपके पास ऑक्टाहेड्रल है, तो नेक्स्ट वी रिक्वायर वन मोर ऑर्बिटल, तो sp3d3 होगा. तो 3 + 3 + 1 7 एटॉमिक ऑर्बिटल्स मिक्स किया तो 7 इक्विवेलेंट हाइब्रिड ऑर्बिटल्स बनेगा. So the geometry is known as pentagonal bipyramidal. So we have iodine, one above the plane, one below the plane. So we have fluorine, pentagonal bipyramidal. So this is the molecules or the ions without any lone pair of electrons.